want to start with a series of statements. The first one here is not too controversial. I think a lot of people agree with this, that machine intelligence is going to transform the 21st century, similar to how computing transformed the 20th century. And you think about how computing in the beginning of the 20th century and the end of the 20th century, like the impact of computers was amazing. It just changed everything from communications, entertainment, transportation, science, literature, arts, you name it. It just, in ways that no one really anticipated. And literally, they couldn't know that in the 1940s, 1950s. And the same thing is going to happen in this century with machine intelligence. It's just going to transform every aspect of society across the globe. Maybe, I think, even bigger than the transformation for computing in the 20th century. Now, a lot of people think this, but I'm very confident in that. The second statement is a little surprising, perhaps. We don't believe that deep learning, which is the current AI technology, is going to be the technology underlying this transition. It's what's hot today, but there's lots of reasons to think that this is not going to be the technology that's going to be driving this forward. I'll get more into that in a second. We're not the only people who feel this way, by the way. I'll show you some quotes. So what is going to be the technology? We think we know. We think we figured out. And the technology that's going to underline the future of AI this century is sensorimotor learning. And that's going to be the dominant AI technology. Very briefly, sensorimotor learning is where you're combining inputs from some sensors or sensory system with the movement to learn models of the world. So humans learn by moving through the world, moving our arms, fingers, and our bodies, moving our eyes. This is integral to how we learn. We're not static entities, and so we learn that way. Of course, the human brain is a sensorimotor learning system, so there's no question about that. And the bet here is that that is going to be the method that we're going to build AI in this century. And then the Meta is building the first developer platform based on sensorimotor learning. We are leading in this, and this is the opportunity that we have. Okay, here's some quotes. Some people. Francois Chollet is a very famous machine intelligence person at Google. He says you cannot achieve general intelligence simply by scaling up today's deep learning techniques. That's exactly what I just said. Jeff Hinton, who's really one of the inventors of deep learning, says, my view is throw it all away and start again, referring to his own creation. Jan LeCun, these are all very famous AI people. He's at Meta. He gets closer to what we're working on. He says what's missing is the principle allow machines to learn how the world works by observation and interaction, moving through the world. This is the biggest obstacle to significant progress in AI. So he's on the right idea there too, although I'm not sure he understands how to do that. Demis Hassabis, who is the founder and CEO of DeepMind, which is part of Google, they're like the 800-pound gorilla in AI. They've also said, yeah, we got to study the human brain because it's the only proof we have for general intelligence. And so they have a bunch of neuroscientists working. I've spoken to Demis. They have a different approach to this, but you never want to count them out. They're working on this too. Jeff Bezos, of course, is not an AI scientist, but I just want to point out there are other business leaders who have similar ideas. And he says humans are just doing something fundamentally different than the current way we do machine learning and machine intelligence. The implication is we probably have to do something different. So this is not a radical idea. So what is sensorimotor learning? These are two sort of cartoon diagrams of deep learning and sensorimotor learning. And I'm showing it to contrast the two. So on the left, you have deep learning, which consists of a series of layers of these artificial neurons. Sometimes there might be 100 layers of them or so. Here I just show a few. They're highly interconnected. And the way you train the system, the way you learn, is you present some pattern of input at one end of this network. You present the desired output or reward at the other end, and you use this technique called backprop, which sort of adjusts all those weights, those blue lines. And you do this over and over and over again, and eventually the system learns the matching between the input and the output. On the right, you have deep learning, sensorimotor learning. You have an input again, just typically from a sensor. But there's a second input, which we call motor, which is really just how the sensor is moving. So you can imagine your finger sensing something and moving, or you can imagine your eyes sensing something at some point in the world and moving. And internal to the sensorimotor learning system, you have a concept of location in a reference frame. So there's an idea that this observation is occurring at some point in space, and then you pair that point in space with the actual observation. And in this case, most of the learning occurs in this pairing between the observation layer and sort of the reference frame location layer. So sensorimotor systems learn models of the world, and they learn where things are relative to other things. The idea of space is critical to how this whole thing works. But that is not an inherent capability on the left-hand side. It's not something you might try to train it on, but it's not there. Let's just talk about how you might go about training one of these systems. So if you take a classic image classifier, for example, you present it a picture of something like this, and you say, aha, that's a car. And then you present another picture and you say, that's also a car. And then you present another picture and you do it, that's also a car. You do this maybe 100,000 times on different categories. Each time you're slowly adjusting these weights very minimally so that you're trying to get the system, and it'll do pretty good at now showing another picture and saying that's a car. On the right-hand side, you wouldn't show a picture of a car. You would be looking at a car, and your eyes would attend to different parts of that car sequentially. So you might first look at one thing on the back here, you say, oh, that's a tire or a wheel. And there's going to be some location in the reference frame. In this case, the reference frame is the reference frame of the car. You say, oh, there's some location on this object where that thing was observed. Then you might move your eyes and look at another thing. This is the door handle. And when you move your eyes, the motor signal tells the internal reference frame to move its location. Since you just moved, you're now tending to a different point in this reference frame, and you're pairing it with what was learned there. And you do it again. You say, now I'm moving my eyes to the front of the car, you update the location of the reference frame, and you pair it with the observation of the headlamp and that's on. And in this way, you build up a model of the car, of its components at relative positions to each other. It's a very different way of learning than with deep learning. There's some real strengths and downsides to deep learning. On the plus side, deep learning in theory can learn any input-output mapping. In theory. In practice, there's problems. But in theory, it can be really, really good. And you can get incrementally better just by using more and more training data. On the downside, it's brittle because you can't train on an infinite amount of data. There's always just points where it fails miserably. You know, you might change a couple of pixels on this blue car, and you don't even see it, and then the system says it's a blueberry. That is the kind of stuff we see all the time. It's very well documented. There's very little ability to generalize because the system doesn't really know what it's looking at. It has no structure about what it's looking at. You know, it's very difficult, and it can't say, oh well, here's another thing with two wheels or four wheels, but it's on a bunch of tracks. Maybe it moves and transports people, things like that. It just can't do that. To get these things to work acceptably well requires unsustainably large training sets, training times, and energy. This is a well-known problem in the AI world right now. Everyone's trying to solve this. Is that it's just huge models that are very expensive to run, that require huge amounts of energy and lots of carbon dioxide emissions. They also aren't good at continuous learning. You can't say, oh, you know what, I now need to throw in another category of my things I want to recognize. If you want to do that, you generally have to start all over from scratch and train the system from the beginning again. But in the real world, things are changing all the time, and you're always learning and updating the real world is always being changed, and these systems can't really do all that at all. On the sensorimotor side, the pros are some of the opposites. They're very robust. They're much more robust than deep learning systems. It's just because of the nature of the way the data is stored. Because you have this structured model, there's an inherent ability to compare models, which leads to generalization. So you can see two different objects have similar components and similar relationships. You might assume that they're doing something similar. It requires much less training data and much more energy efficient. Training is fast, and you can learn continuously without forgetting other things. So you just can constantly add new things and change things, and it's no problem at all. It's interesting, the models are also actionable in the sense that since you have a structured model, it's possible to do things like planning and thinking, where you can say, how would I achieve a certain result? And you can say, well, to achieve that result, I have to move here and do this kind of action, things like that. The downside is it's not always the best solution, especially for point problems. So if I want to create a system that does, plays the best game of Go, I'm going to use a deep learning system. It's always going to be the best. They've already beaten humans, the best humans, and you can't beat it. And so, I wouldn't want to use sensorimotor learning to do a point problem or play a game or even recognize images because in theory, you can do better on deep learning. So in summary, the deep learning systems are best for point problems. That means narrow domains, no general knowledge required. Sensory learning systems are best for general problems that require knowledge and understanding of the world. And that is the big thing that's missing in today's AI. That's what everyone is critical about it for. Just one slide on neuroscience here. We didn't just come up with this. We actually have been studying the brain for many years, and we figured out this is how the brain works. And so I'll just give you a little very brief background here. That's a picture of the neocortex, which is the organ of intelligence. It's a sheet of materials. If you could look at it under a microscope, you'd see that it's actually composed of these columns. There's over 100,000 columns in the human brain. These are like the size of a grain of rice. They don't look like this, but you can visualize them this way. And all the different parts of the neocortex look like this. It's surprising, and even parts to do vision and touch and hearing, they all look like this. They have these column structure. These are a cartoon drawing of 3 of those columns. We can say that they all have a sort of complex architecture. They all have the same prototypical layers and cell types and connections. And so the big mystery is like, what do these columns do and how does this lead to intelligence? We had our first big discovery here, or one of our big discoveries, is that each column in the neocortex is a complete sensorimotor learning system. That was not understood. Question? No? Okay. But if you have questions, just stop. Okay. Became most learning system. So going back to that picture I showed you before, and I said there's a reference frame and then there's an input. We see that in every cortical column, and we propose that there's a layer of cells in every cortical column that's a reference frame. These are the grid cells. And at the time we made that prediction, and that's almost like a radical idea, but now people are finding it in many places in the network. The second discovery we had has to do with how these columns collaborate with each other. And so there are these long-range connections in the neocortex that I show here with these horizontal green arrows. And this is the way the models collaborate with each other. This is how they talk to each other. You can think of it very simply as they're trying to reach a consensus on what it is they're seeing and where it is in the world. And so each column has got its own modeling system. It's getting its own input, and yet together they can come to this general consensus. This is this basic architecture of the neocortex, and this is the architecture we're going to use in our Monty system. This has been documented in a series of neuroscience papers. It's done extremely well. Richard Dawkins heard about the theory. He said it was brilliant. He's a famous biologist. He wrote a nice foreword to my book. Bill Gates took the book, my book from last year, and did one of the top 5 he recommends. The only nonfiction book he recommended. Pretty thrilled by it too. Okay, so let's just talk about Monty. Monty is a code name. It's based on the name of a scientist called Vernon Mountcastle. That's where we got that name. And I think of it as a developer platform for sensorimotor AI. How would you build sensorimotor AI systems? And the basic idea here is these systems are built using 2 types of modules in varying combinations. The first module we've already seen. We call this a learning module. It's more complicated than this, but basically it's the idea that you take an input, you have a motor thing, which is how the sensor is moving, and you build these structured models through movement of a sensor. These can be very flexible. They can model different things. They can model objects like, a soda can or a computer or a mouse and, a chair. They can model environments like rooms and outdoor spaces. In your brain, the columns also, these learning modules also model your body. So you have some of these are dedicated to modeling the space around your body. Pretty much anything with structure. And this is how the brain can learn things like math, history, and language. Even though they don't have physical structure in the world, they have internal structure. And these, if you use the reference frame right, you can learn any structured model space. That's not a speculative idea. We know that this is how, we know brains do this. And if we're right about sensorimotor learning, this is the method they're going to do it. The second type of module we'll call a sensor module. It's a bit different than you think of both sensors. I'll explain as we go into this. First of all, notice there's 2 outputs from the sensor. There's what it's sensing, we'll call that the output, and then there's also how it's moving. It's going to tell the world, I'm moving this way, I'm moving that way. And of course, that matches up really nicely with the learning modules. There's the idea that you have both the thing that you're sensing and how the sensor is moving. This learning modules can work with any type of modality. So we have biological modalities such as vision, touch, hearing. Bats do echolocation. But it would also work with LiDAR, radar, ultrasound. It really doesn't matter. As long as it has the right sort of output, it'll work. Now, here's the key idea. Sensor modules are not like a camera or something like that. They detect features at locations in 3D space, one at a time. When you look at the world, you don't actually see a picture. You actually, even if you're not aware of it, your eyes are attending to different points in space, and you know where they are. If you're looking at me, I'm at some distance from you in some orientation. It's not like that starts right at the beginning of the system. The locations in space where things are being sensed. So they sense what is sensed and how the sensor is moving, and then the learning module has to figure out how to map that onto a reference frame. And because all sensor modules share an understanding of space, they can be largely interchangeable. That's why the cortex can process touch and vision in the same way. You know, my finger has a location in space when it's touching something, and my brain, it tells my brain how it's moving when I move it over an object. But the same thing happens with your eyes, and my eyes can report where they're sensing something in space and how they're moving. And that's why we can intermix all kinds of modalities in our brain. They're treated the same in some ways. Okay, now there's another thing going on, which I hadn't mentioned earlier, is that this motor signal is bidirectional. So the learning modules can output a motor signal saying, here's how I want you to move. And the sensor modules can input this motor signal. Now, think about it this way, you know, I could be exploring an object with my finger and learning how it feels, but I can also, now that I have a model of the thing, I might say, okay, I want to hit the power button on my cell phone. Well, the learning modules, I know where that is. I'm going to tell somebody in the sensor world, like, move your finger there and move it in this direction. And so this is essentially, the entire system is robotic from the beginning. You don't have to use that component, but in the future, AI and robotics are really going to be one field, and the sensory model learning is going to achieve both of those goals. So that's the basic idea. Now, Monty applications can scale in multiple dimensions. And so we see, what I'm about to show you are things we've seen, and we know that these are the kind of things we see in mammal brain. The simplest thing we just talked about, you could have one learning module and one sensor module. And actually, this could be quite useful. It's not like this is a stupid idea, but typically you might have more. The first way you could change in different scales, you go to multimodal. You can say, okay, now I'm going to have two different types of sensors, maybe touch and vision, or LiDAR and vision, or something like that. Each of those is going to be going to its own little learning module. And yet, because of that voting layer I talked about before, they can collaborate with each other. So one modality can inform the other and back and forth, and so you could mix and match them as we do all the time. This makes the system more robust. So, for example, if I was using a vision system and now I'm in the dark and I really can't see very well, I can supplement it with another modality. And it makes for faster inference because now I have two things trying to resolve what's going on at once. You can expand this in a horizontal or wider realm. So you can add more modalities, more sensor modules to the same modality and more models. So think about it this way. Now I have 4 fingers on the left there, 4 touch sensors. And so if I'm using my index and thumb on 2 hands, I can do a lot more, a lot quicker. I can learn quicker, I can infer quicker, I can manipulate things better. On the vision side, I get more acuity. So we see this kind of like expansion in the horizontal direction. You can also go deeper, so you can put models on top of models, like in a hierarchical form. And so you essentially represent hierarchical knowledge and you get deeper insights. Just to give you a sense, in general, it's believed that humans have a 4-level visual system like this. And mice have a 1-level visual system. And mice can do a lot of sophisticated vision. They can go out and see different things. They recognize what's food and what's not food. They can know how to grab that food in just the right way so that when they bring it up to their mouth, it's in the right position to eat. And then they can look at it and eat different pieces, just like you would like an apple. And they can do that with a 1-level visual system. So you don't have to go deeper to do some very sophisticated things. And of course, you can go deep and wide. This is what we see in, you get more of this as you get into like the higher animals, and humans have very big, large neocortex. And these give you deeper insights in multiple domains. So this is the general, very high level plan for how this works. The good news is we can start small. we don't have to do all this. We can, even a small systems can be powerful, and but we can design the architecture to support this kind of expansion, even if we start small today. You know, to really build human level brains, we might need to do all this stuff in silicon, and there might have to be these modules that have to be built into silicon and so on. We may not be able to do this with software, almost certainly not. So we can expand as that becomes capable. I have one last slide here, and this is sort of like a strategy for how we go forward. First of all, I think there's an opportunity here to establish a leadership position. And this is one of the key things every startup wants to do, every new technologist wants to do, well, any startup wants to do, is establish a leadership position in a field. So AI scientists know we have to go beyond deep learning. Most people don't understand what to do next. And Numenta we have a multi-year head start on this. I don't know how many years, but it's a multi-year head start. People will catch up to us eventually, but right now we're ahead of this. So we have the opportunity to define the field, define the terminology, define, you know, what this technology is and what it's good for. And that is always a tremendous thing to have, that opportunity. We're not trying to fight our way into an existing field. We just don't want to go where the other people are. We're going to create new territory here. I always felt it's important to focus on developer platforms from the start. And you can have the best technology, but if someone else comes along later and makes it easier to use, you lose. There's so many examples of this in technology. So it's not good enough to have the best technology. You also have to make it so that nobody can just outrun you like, hey, I made this easier. So we have to focus on that from the start, in addition to the technology. I think from an application space, you need to pick one, maybe two application areas to begin with. We can start very small. These don't have to be flashy applications. They don't have to like rock, you know, the world. They have to show some commercial value. I mean, somebody says, I want to use this, I'm willing to pay for it. And it has to demonstrate the principles of Sensorimotor AI and the Monty platform. You know, whenever you create a new platform, I've observed this both in my own world and other people, there's always a whole bunch of people who want to rush to that and see what it can do. And so you just have to get it going, and they will do that. They'll come, but it's got to be easy and it's got to work. So, you know, whether that's self-driving cars, we could do stuff like help the vision system self-driving cars, whether we do robotics, whether we do multiple sensory security. I don't really know yet. We haven't really chosen what these application areas to focus on. There's lots of partnering opportunities. So over time, which is great for a platform. So people who make sensors might want to modify those sensors to be compatible with Monty and to really be sort of location aware. And so there's an opportunity to partner with them on that. There's opportunity to partner with people in building new types of learning models that work on slightly different variations of the technologies or pre-learned or have certain biases. There's opportunities to work with silicon vendors to implement this stuff. We already have conversations on other parts of our work. There's opportunities to work with systems integrators who can take this and then help, you know, less capable end developers, and then of course end developers themselves. So in summary, we have the opportunity here to basically create and shepherd so one of the most important technologies of the 21st century. I think it's exciting. I think it's also it's something we have to take very carefully, thoughtful about, because it's really going to have a big impact. And we have to think carefully how we handle that. But it's a tremendous opportunity. We have a lot of issues we still have to resolve, but I think everything I've just told you here is pretty clear. And that's how we're going forward. That's it.